And we'll start from current slide. Okay. Okay, I can't think of any major announcements that I've seen coming down the pipe, so I will just go on and get started. Today we're in Chapter 12. We got started in it last time, Matter, and 12.2 are Properties of Solids. Last time we looked at the three phases or states of matter and described them. Now we're going to take one at a time, and 12.2 will be talking about properties of solids. Now we're not going to go into enormous detail here, but just enough for you to get an idea of what's going on here. Any questions before we get started? Okay. So to start with, there's several properties mentioned here, and I'll do them one at a time, sort of like the book does. The first is the property of, let me get my pen set up. I forget to do that. Okay. Cohesion versus adhesion. All right. Now, cohesion is basically referring to the force of attraction between like molecules. Okay, remember we've talked a little bit before about the surface tension of water and how strong that is. Water shouldn't even be a liquid. It should be a gas because of its light atomic or molecular mass, but it's a liquid because those molecules hang together so tightly. That's an attraction between like molecules. One water molecule hangs on to the next one, hangs on to the next one. That's an example of cohesion, okay? There are other examples too you're probably familiar with, and this is Felista, right?
Yes, sir.
Okay, good deal. All right. Am I pronouncing that right?
Felista,
Yeah, okay. 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 So, cohesion, the force of attraction between like molecules. Adhesion, on the other hand, is the force of attraction between unlike molecules, okay, or different molecules. Okay. Now, probably a word that you're fairly used to. Okay. And is it Kalisha?
Yes, sir.
Okay, I thought so.
You got used to all the names now.
I'm getting close, but just wait till next week. I'll forget them all. Okay. Yeah. Okay. Adhesion. You might be able to think of it this way: what does an adhesive do?
I was just about to say that.
Right. It sticks to things generally that are not similar. So that is adhesion. Okay. Now, why do they mention that here? Well, solids, in being solids, their bonding is really, really, really strong. Okay? And so, like molecules, or unlike either one, they bond together very strongly. That's why they keep their own shape. That's why they have a fixed volume, because they do cohere and adhere very strongly. Now, another principle or property of solids is, and by the way, cohesion and adhesion, I just gave the example of cohesion of water molecules. They exhibit cohesion as well, and to some extent some adhesion too. But now the next one is tensile strength. This is a solid property only. Okay? It's the tensile strength of a solid is a measure of its resistance to being pulled apart. I can't write. Oh, good deal. Thank you. Okay. Let me pause just a moment here and make sure I put the key with this so when I get home, I won't, well, yeah. If I don't get started on it at home, I won't wind up someplace. Okay. All right. Is that first one also? Yeah. Okay. Good deal. So, here's what we mean by that.
Is that TONSILE?
Where is this? TENSILE, tensile strength. Tensile, think of the word tension. You know, that's pulling on something. You're giving it tension. Like guitar string, if any of you play the guitar, but you see how they fiddle with the thing? They're adjusting the tension of that string to get the right sound from it. Well, tensile strength is a measure of resistance being pulled apart. All solids will exhibit this. Obviously, liquids and gases don't have any resistance being pulled apart. You can splash them. I can't easily pull apart any molecules in the air because they don't have any sticking together anyway. Okay, but a solid will have this. Think of playing tug of war. Okay, yeah, you're pulling on a cord. You're glad that cord isn't going to break on you because otherwise the strength you're pulling, you're going to fall all over your teammates, you know, something. So the resistance to being pulled apart. Now they give a little formula here. They don't do anything with it. They measure this tensile strength, or actually the tensile strength is a ratio between the force required to break a rod. Tensile strength is the ratio of the force, I can't write, required to break a rod divided by the cross-sectional area of the rod or wire. Okay. So, say you have a material that you've extruded into a pipe, a rod, you know, something like this. And they actually have these tools to pull and pull and pull on that until they break. They're measuring the force needed. So when that does break, they register the highest force that was required, divide that by the cross-sectional area. That's the tensile strength of that material. And it's a pretty uniform type thing. Of course, a smaller cross-sectional area, it's going to be easier to pull it apart.
That's going to be the middle, right?
What's that?
The cross-sectional, that's going to be the middle part?
Well, a cross-sectional would be, if it's a pipe, it's whatever the cross-sectional area is. Take the diameter, divide by 2, and multiply by pi. No, I'm sorry. The diameter, yeah. Divide it by 2, that gives you the radius. Square the radius times the pi, and that gives you the cross-sectional area. Usually that will be given, well, we're not going to do any problems with it, okay? Now, as they show here, it actually makes it look like, and it has to be, if it is stretching this thing in any way, that means it has to be reducing the cross-sectional area because it's, you know, and so you take the cross-sectional area before you start stressing it. And then that's the, that. And again, we're not going to do any problems with that, okay? Another characteristic or property of solids is hardness. Any of you ever used before yourself or a baby or something talcum powder? You know what I'm talking about? You can't imagine anything much softer than that, can you? That is number one on the Mohs hardness scale. Softest material.
Now,
They're what?
they causing problems. They say it's caused problems for females and
Oh, really?
Yeah, and they taking it. They I think Johnson and Johnson getting sued.
Oh, really?
Yeah, talcum powder. Yeah.
Yeah. Okay. Well, that is a very soft material. Of all the solids, that's number one, the softest material on the hardness scale. Now, they don't seem to be talking about this. They're talking about the Brunel method. I think it's how you name it. Named after Johann Brunel, common industrial method to use to measure hardness of a metal. You place the metal, a mass is placed on the object. The mass placed on the object in kilograms divided by the surface area of the impression in square millimeters. Okay? And so this is different from the Mohs hardness scale, which I was going to mention there. Johann Brunel was an engineer and metallurgist born in Sweden, and he came up with this machine. And I believe, no, okay, I thought that might be it there, but it's not. And again, you're not responsible for this, don't sweat it, but the hardness of a solid is a measure of the internal resistance of its molecules to being forced further apart or closer together. It's the measure of the internal resistance of a material's molecules, to being forced further apart or closer together. And don't sweat these too much. This is just to get you familiar with terminology. Okay. Now, that sounds somewhat similar to tensile strength. But tensile strength is talking more in terms of rods or wires. This is talking about any solid. Okay. An example is the scratch test. Okay. I don't know if you can imagine, if you had a piece of talcum, you could scratch it and just break it off. It is that soft, okay? Now, a little bit harder than that, this is called sheetrock. Actually, inside that is a material called gypsum, and that is, again, something you can scratch off. Not as easily as you can talcum powder, but still you can scratch it with your fingernail. But most other materials, you beyond that. Like, I can't scratch.
It gets really wet, doesn't it? Like, because I've seen it breaks apart.
Yeah, and it breaks apart even easier. Mm-hmm. But then it starts dissolving, and it's no longer considered a solid then. Right. So you're considering the solid when it's hard. Now, you can scratch to your heart's content on this piece of aluminum. You're not going to make anything. Now, you might get a chisel into it, and then you would. Well, because steel, the chisel, is harder than the aluminum. So you see, that sets up the scale. So this is what hardness is, the measure of an internal resistance of the molecules to being either forced apart or crammed together any more tightly. And the Brunel method is this. You place an object, a mass placed on an object, now, I like the way they say placed on an object, divided by, that's mass, okay? Goodness gracious, this is aggravating. Okay. Mass placed on an object divided by the surface area of the impression. Okay. So, basically, that's a pretty ugly impression there, but that's two S's and it doesn't look like but one. Okay, impression. All right. This chair I'm sitting on has a softness to it. Thank you very much. So I can press on that with hardly any mass at all and then measure the surface area of the impression that you got. You'd find that it's a really soft material. Whereas if you did the same thing to these plastic chairs, you might be able to measure a little bit of an indentation there. Try to do it to the desktop. It's going to be quite a bit harder to make an indentation there. But you can imagine you can put a big enough mass on it that you do start indenting it just a little bit. So if you take the mass placed on an object and then divide that by the surface area of the impression, that gives you the Brinell ratio. Again, don't sweat it. You're not going to be required to do it. They do have a picture of a Brinell hardness testing machine, and you can just see that and go with it. Now, let's go to a new page here. So, y'all got all this so I can erase it? Okay. Another property of solids is ductility. Does that mean anything to you? What's that?
Like duct tape.
Okay.
Yeah,
All right. Actually, I've sort of referred to it already before, but you see, duct tape is used to tape up air conditioning ducts. That's where it gets its name, only they've changed it to duck, D-U-C-K. That's a brand name, but originally it was a duct tape, and since it sounded a lot, the company named it duct tape. And the ducts are what's important there. The ducts are the enclosures through which a fluid flows. Now, to be ductile means you can stretch something out into something. It's kind of the opposite of the tensional thing. It's how that resists it. The ductility is the ability to be stretched. Okay? Here's the formal definition. The property of a metal, now we're talking about metals mostly now, property of metals, so not all materials would have this. Like a ceramic would not have this at all. Property of a metal, but you want metals to have this, that enables it to be drawn through a die Now, do you know what a die is? There's a couple of different dies, okay? One die is a single, a pair of dice. One of those is a die. Okay, that's not what they're talking about here. A die is a hole, basically. And you're pulling the metal, obviously once it's been heated somewhat, through a die. And it doesn't have to be heated. Through a die. And the ductility would be the ability, a property of a metal that enables it to be drawn through a die to reduce a wire. Okay? One very ductile metal is copper. Copper can be drawn into wires, and you can get those wires into tiny little filaments. So copper is quite good at it's a very ductile material, meaning it can be drawn into a wire. It's one reason it's so useful for wiring, okay? And actually, when it's drawn through into a wire, it's also bendable, which makes it really good. This is all copper wire in here. There's wire carrying the juices here all over the place, but they can bend, and it doesn't distract from it. Now, you don't want to sit there and do this to it, because ultimately that will make it break. Being ductile doesn't mean it's indestructible, but it can be able to produce a wire. Like I said, some materials, non-metals, can you imagine trying to do this to glass or a ceramic material? No. You try to do that, it's going to shatter. Okay? So a ductile material is a metal that can be drawn in. Silver, for instance, is a better conductor than copper, not by much, but a little bit, but it doesn't, it's not very ductile. And even when it is, it's very brittle, so it's hard to bend and use like copper wire would be. Okay?
I wonder why they decided to make all the coins silver except for the penny.
Okay, actually they're not. Some of them originally may have been silver. But nickel is made out of, or originally was made out of nickel, not silver, okay? The dime may have been silver because it's much smaller than the nickel because it's more valuable, but silver is much more valuable than nickel is. So a bigger nickel is bigger than is less valuable than a smaller dime because it probably originally. Now they're not. If you look at just about any of the coins, the silvery looking coins, but even, like you said, the penny, since we're talking about that. Look at that quarter, and on the edge, you see it's not silvery looking. It's a cheaper metal in the middle. Because what they used to make quarters out of, that was a quarter's worth of that metal. Now it's gone up so much in value, that would have been several dollars worth. Well, they don't want the quarter to be, the material in it to be more valuable than it's supposed to be. Otherwise, people would melt it down and sell the material. So they,
it's lost its value pretty much.
Yeah. And now nickels, I think, may still be nickel or whatever alloy they have that looks like a nickel. But even the penny that you mentioned, that's no longer copper. Copper is more valuable than a penny now, so they mix a cheaper metal with it as an alloy to make this. So all the coins pretty much, I don't know for sure about the nickel, but all the other coins, even that dime, if you look at the edge, you see it's a cheaper material in the middle of it. The nickel may still be nickel or whatever metal they started using in place of nickel. But in general, the coins aren't what they originally were because that size of that material would be worth more than the coin was. So then no one would use it as a coin.
Makes sense.
What's that?
It makes sense.
Yeah. Okay. So that's what ductility is. As the rod is pulled through the die, the diameter is decreased and its length is increased until it becomes a wire. And that's what the whole purpose is. Now, you usually heat it up first to do that. You don't do it cold, but you could do it to some extent even then. All right. Now, fairly close to that is malleability. Okay, I'm trying to make sure I get the spelling right. Property of a metal, again of a metal, okay, that enables it to be hammered and rolled. I didn't spell hammered right. And rolled. Okay? Into a sheet. Okay? Now again, if you add enough heat, you can do this to just about any metal. Okay? But the lower the temperature, the more you can do it. It's even better. Gold is very malleable. Pure gold. This ring is not pure gold, I guarantee it. If it was, it wouldn't have this perfect or near perfect shape, okay? Because it would be so, I could do that to it and make it squeeze, okay? Because gold is very malleable. So, most jewelry is 14 karat gold, whereas 24 or 25 karat is pure gold. Now, in India, they make a lot of jewelry with pure gold, okay? And if you ever get a necklace or something that was made from that, you better be careful because it will stretch. Well, be careful, it might get stolen. But it will be stretched because gold is very malleable, and if you have a heavy pendant on it, it's going to stretch that, and it'll break easily, and then you've lost this golden necklace, okay?
Can they remelt it down or whatever?
Oh, yeah, you can do that and make it into a chunk. So, yeah, you don't want to mess around with too much gold. It's way too valuable. And so that's the other thing. This is cheaper. I like that too. But it's also harder because malleability means you can roll it. Now, think of a metal that must be very malleable. Gold is probably the most. Have you heard of gold foil or gold leaf? Okay. That is so thin, you could just sort of press it onto another material and it looks like it's gold, you know, but it's so very thin.
I wonder if it's true, like I've seen where people say they put it on different boots and stuff. Have y'all seen that before? Put like little thin little sheets of gold on food.
I seen the ice cream.
Yeah, the ice cream, right.
He
Yeah.
said he had paid like $6,000 for his bowl of ice cream, and it had gold flakes all over it.
Right.
It
What
even had a strawberry that was dipped in like chocolate gold or something like that. But he was like, I can't share this ice cream. And he showed me the receipt and he had paid like $6,000 for that.
Well, I don't want to say anything about what I would think of his intelligence because, number one, why ingest something that is that valuable and does you absolutely no good? You know, if anything, it may do you harm. Now, I've never heard of.
I didn't want to flush that when it came out.
Yeah.
$6,000 ice cream.
Yeah, that's just someone with more money than sense. Okay.
Right.
Well.
If I ever get a hold of someone, I keep it.
Yeah. Well, of course, we got some people around who have gold toilet fixtures. We won't name who that may be, but anyway. So that's malleability, okay? And here is another one that you probably haven't thought of, aluminum.
That's cheap, right?
It's pretty cheap.
Yeah.
And what do you do with very thinly rolled aluminum? Aluminum foil, exactly. Okay, exactly. And that thing they used to, I don't think they do this anymore. Chewing gum sticks, they used to have aluminum.
Some of them do.
They still do. They
Yeah.
still have that. That's very malleable material. Okay? Elasticity. Now, this is one that's pretty important. When you think of elastic, what do you think?
Rubber band.
Yeah, rubber band, and you think something that'll stretch.
Yeah.
That's what we think elastic. Really what elasticity is the ability to return to its original shape.
Yeah.
So yes, the rubber band will stretch, but what's more important, if it's elastic, it will return to its original shape.
Right.
Okay? If it doesn't, that means it's not elastic, okay, or somewhat inelastic. So that's what it goes to. The elasticity is a measure of a deformed object's ability to return to its original size and shape.
You know what? It makes me think about something. Like, have you ever squeezed an egg, but not like squeeze it enough to pop it?
Right.
Like, would that be considered to be still like elastic if it doesn't pop, like bust open?
Yeah, but it has a pretty low because if you do too much, it's going to fracture.
It's like squeeze.
Like, I've done that before. Like, I've squeezed it, but it hasn't like bust open. Like, it'll just go back to its original round shape.
Yeah.
But of course, if you squeeze it harder, it's gonna pop.
And there's two things to do with that. It's not just how hard you squeeze, but the rate at which you squeeze. If you do it really quickly, it's going to crack too.
Right.
If you allow it time to adjust, but then if it does come back, that's a measure of its elasticity. But of course, an eggshell fractures pretty easily, so it doesn't have a high elasticity. A diving board, you want that to be really elastic, so you spring on the springs. You want to come back to their original shape, so that's what we use elasticity for. So it's a measure of a deformed object's ability. Ability. Oh man. I abbreviate like crazy, like ability. I just left off a whole syllable, okay, to return to original size and shape.
Maybe a mattress. I don't know.
What's that?
Maybe a mattress, like a memory
Yes,
foam
right.
mattress or something.
Exactly. So some would argue that might not be a pure solid, but yeah, it's still.
Yeah.
But yeah, that's the general idea of it. This chair has a little bit of elasticity to it. I can lean on it, and it does move back a little bit, but then it comes back to its original shape. I'm sure we have a nephew that when he was much younger, we had bought a computer desk, and it wasn't a super valuable one by any means. We were going pretty cheap. It was early in our marriage and stuff, so we got a good deal. We had to put it all together, and stuff. And Dan came to visit us. He must have been 3rd or 4th grade, something like that. Of course, he was playing on the computer game. He was, here's what I picture happening. I didn't actually see it. I think he was hanging on to the handles of the drawer, and doing something, and broke the handle because it was cheap. We admit it was cheap. And when he talked, he said, "But I didn't put my full weight on it." So okay. I don't care if you put it's cheap material, but yeah, it would deform for a little bit, but then after that it would fracture. Elasticity is the ability of a material to return to its original shape without, here is the next term under this is elastic limit. Every material will have this, and they have devices to measure this too. You press on it and it does deform, When you release the stress, it goes back. As long as it goes back, that's elastic. Press more and more, as long as it goes back, that's elastic. But at some point, one of two things is going to happen. It fractures, you press too hard, and it actually breaks. It will not go past that, so that would be an elastic limit. Or, the other thing, it bends permanently. And that's what we call plastic. And then it becomes plastic, not returning to its original shape. So we usually think of plastic as something like this chair seat, Well, that has been molded into a shape that wasn't its original shape. So that's its plasticity as opposed to elasticity, Elasticity returns. Plasticity, you do it so much, it doesn't return. Now, I think you could imagine if I took a heavy enough sledgehammer and ping into that, it's going to bend and not come back to original shape. That would be past its elastic limit. So the elastic limit of a solid is the point beyond which a deformed object cannot return to its original shape. Point, I'll just put point, past which, what's that? Yeah, I started to spell it out, but I decided to put PT, but then the O showed up. I don't know. Past which it will not return. To the original shape. The problem with this thing is I hit the board and there's always a lag time before it shows up. So I have most of a word written before I realize that I don't have the letters spaced well because it doesn't show up on here as I'm writing. It sort of drives me nuts. So anyway, that's the elastic limit. And we want, and here's where we get to the other slide. All right. Come on. Yeah, here we go. This is a spring. It looks like a pretty sturdy spring, though. In fact, that reminds me of the spring on our garage door opener. Pretty heavy-duty spring, okay? And you can stretch this thing, and it takes a lot of force to stretch it, and usually it returns right back to its original shape. That's its elasticity. This one has been really stretched out here, and it says here it's stretched near its elastic limit. If you release that, it will go back to here. But this one, they say, has been stretched beyond its elastic limit. In other words, when you release it, it stays looking like that. And that reminds me sort of that rubber band idea, you know, that stretch it too far and it won't go back to its original shape. It's now a little bit longer and thinner and stuff like that. If you stretch it way beyond the elastic limit, the break occurs. Now, some materials are very brittle, and that's not really a formal term, but that means you stretch it and it doesn't really go to a plastic state. If you stretch it too far, it's going to fracture here, just at the elastic limit. You know, it's not ever going to deform. Okay. Glass is a lot that way. Okay. It's not really a solid, but other things like that, the porcelain, you know, your dinnerware, you know, there's not much much elasticity there at all. You do it too much, it's going to crack. It's going to break. Okay. So this is what's meant by the elastic limit. Okay. And then at some point, anything is going to stretch beyond it, and then it breaks. And that's called fracture. Okay. Now, let's go to, let me just see what the next concept. It's coming up soon, but let's go back to our thing just to get the definition down first. All right. I've been using this term already. Let me get my pen back. I have to do it every time we go back and forth. Stress. Okay? What a stress is the ratio of an outside applied force, which tends to cause a distortion, to the area over which the force acts. So this is a ratio of a force, of an applied force, can't write, which tends to cause a distortion to the area over which it acts. Okay, the force acts. Okay, now that has, what's that? I'm sorry, if I make a period or something like that, it thinks it wants me to go to another slide. You know, watch this. Oh, it didn't do it that time. Now it won't do it, but if I've been writing and make a period, it sometimes flips to another slide. Okay, so here is, I sort of wrote it here, applied force, it's a ratio of applied force to the area over which it acts. Here is the actual formula. This one we will be doing somewhat. Force divided by area. That's called the stress. Okay? Now, what are the normal units for force, say in the SI system? Newton. Okay? And area would be, technically, in the SI system would be square meters. Now, that's a mighty big unit. Okay? And a Newton's a fairly small unit, okay? So that would be an incredibly small, and I apologize for this. They're calling it stress, and in a couple of pages, they're going to call it something else. I thought, well, maybe not. Maybe they're still going to call it stress. Yeah, they still call it stress. But another name for it is pressure. Pressure is also stress as force per unit area. And why they call it stress here rather than pressure, I haven't figured that out yet. Okay? Because the much more common name is pressure. So I'm going to put a P in front of here too for pressure. The book calls it stress. It's also pressure. Okay? Now, this is Newton per square meter. Now, since Newton is a fairly small amount and meter is a huge area, okay, it doesn't take much. This would be a very small amount of pressure, 1 Newton per square meter. I'll give you an example for that. If someone were to open that door, is it open or closed now? Open. Okay, let's say close the door and do a little bit of pressurization in the room. You could measure that in several pascals. I don't feel a thing, okay? So in order to really do a measurable amount, and by the way, this is called a pascal, P-A. I'm trying to think now what the symbol P is used for. There's some other unit already had the P, so this is Pascal. Okay, named after, and this is why it's capitalized, at least the P is, after Blaise Pascal. He was a French, I believe, and believe it or not, a mathematician, a physicist, and a theologian. Okay. Yeah, that's a real Renaissance man. Born in France, he invented a calculating machine that was later called a Pascaline. He invented the barometer that we use to measure air pressure. That's why they named the unit of pressure after him. Hydraulic press, which produces stress or pressure, and the syringe. He invented that, okay? Quite a good scientist. Mathematician, there's several, Pascal's law, Pascal's triangle. There's just so many things with his name attached with it. But he was a theologian. So he really didn't publish a lot mathematically or scientifically, though he did do some. He was just a great thinker, you know. Now, if you'll think of this also, and this even extends into more modern times, quite often our better, or for a while, let's go back to the Dark Ages. In Europe, the only thing that kept learning and education alive in the Dark Ages, most of everybody were totally illiterate then, except where? The church. The church had to keep copying manuscripts and doing things. So for a long time, your theologians were some of the brightest people because they had the most training, the most education. And that has continued, and I don't mean anything negative by this, but that continued in the black culture, because if you think about it, during slavery, it was hard for them to keep someone from reading the Bible. So the preachers could get education, whereas most of the rest of the occupations were not allowed to have. So, and I remarked at this, I was sitting at a table at a professional meeting we had before one of the terms began, and there were we had an eating meeting, so we had lunch and stuff, and I was sitting at a table. I was sitting with Mr. Walker, who taught, he's retired now, but he taught art, and I knew he was a pastor. I was also with Mr. Roosevelt Williams, who's commercial art over on the Birmingham campus, and then another guy, I didn't know him very well. In fact, I just met him at that table. I don't remember him now. He's already retired too. We were sitting there talking and laughing, and then this other guy said something, or Mr. Walker said something to him. I said, "Goodness gracious, you're a pastor too?" And he said, "Oh, yeah." So I turned to Mr. Williams and said, "Hey, they're ganging up on us here." He looked at me and said, "I'm a pastor too." So I was just amazed at how many pastors are also teachers here at the college, because they were in many senses, some of the most educated, but they got other education too. And part of the reason of that, because very small churches sometimes can't afford a full-time pastor, so they have to have bivocational pastor. So I say, oh man, the hounds of heaven, they're after me. Okay, so, but that was reality here. So Blaise Pascal, it really wasn't too surprising. He was also a theologian, because he was a very well-educated man. So a Newton per meter squared is called a Pascal. And like I say, a Pascal is a tiny amount of pressure. So most of the time when we're measuring any great amount of pressure, we're going to measure in kilopascals, which means, kilo means 1,000. So thousands of pascals. So when you go out and look at your tires to see if you've got enough air pressure in them, you'll usually see two numbers there. One of them is so many PSI. Well, what does PSI stand for? Pounds, that's your force, per square inch. Okay? Inches squared, that's your area. Pounds per square inch, that's a PSI. Well, most tires, I would say, I'm just going to give a ballpark, say 32 to 40, 60, maybe even PSI would be the normal pressure for them. That would be a bigger number of kilopascals, okay? Thousands of pascals to make 1 PSI. Thousands of them, okay? So you see a PSI is a fairly reasonable amount of pressure, because that's per square inch. A square inch is basically the area of your two thumb joints together. That's a square inch. And a pound per square inch, that's a fair amount of pressure. A Newton, which is smaller than a pound, in a square meter, which would be basically the area of that door beneath the knob. That's a huge area, okay? So a Pascal, very small unit, so you need to have kilopascals, but even a kilopascal is smaller than a pound per square inch. I hope I'm saying that right. Yeah. Okay. Now, here we go back to the other slide. Sorry, keep going back and forth here. Okay. Come on. You can do it. Yeah, there we go. All right. Now, here is a tabletop of some nature, and I placed, or they placed, a brick on that tabletop. Laid it down this way. Now, this brick is 16 centimeters long, 8 centimeters wide, 6 centimeters thick. This brick is 6 centimeters thick, 8 centimeters wide, and 16 centimeters long. Identical bricks. Identical mass, identical weight, identical every way. 3 holes, everything's just the same. Okay? So everything's identical about this brick except how it's placed on the table. Which of these is going to create the largest stress on the table?
The bigger one?
No, they're the same size.
The flat one?
The flat one, actually, it's less because its force is its weight, and its area over which it's acting is 16 by 8. 16 this way, 8 this way. 16 by 8 is, goodness gracious, 96 maybe? I think that's right. 96 square centimeters. Whereas this one, it's on the end that is 6 times 8, 48 square centimeters. So this will have twice the pressure of this one because it's the same force per smaller area. This is the same force per larger area, so that way. Now here's, and they'll get to this in the next thing, but I'm going to give it to you now. I was dancing with my darling, okay, and she accidentally, and she was wearing spike heels, okay, and she accidentally stepped on my toe. Ouch. I was dancing with my darling, same one, by the way, identical, except she was wearing sneakers, and she stepped on my toe. Which hurt worse? Yes. Which would you think would hurt first, huh?
The sharp one?
Yes, the spike heel. Why? Because she had the same force, weight, but the spike heel was on an area about like that. The sneaker was on an area about like that. Okay? So, same weight, smaller area, more stress. Same weight, larger area, less stress. Okay? That's what we mean by stress, which is another word for pressure. Okay? And this is, let's see if they give this example. No, they don't. Okay? Let's do this example right here. It's given in your book on page 317 by case 1 and case 2. Okay? The weight of the brick is constant, but the stress on the table is this. Okay, here it is. I had to find it somewhere. Imagine a brick weighing 12 newtons. So this is the weight, which is force F sub W, force due to weight. That's 12.0 newtons. That's this brick. It's also that brick. They both weigh the same. They're identical bricks. Okay? First lying on its side on a table and then standing on one end. The weight of the brick is the same no matter what its position. In fact, they're saying this is the same brick. I mean, it's not even identical bricks. It's the same brick. We just put it up there in different ways. Okay? The position of the brick does make a difference, not on the weight on the table, but on the stress of the table. Okay? And in which case is the stress the greater? Okay? Well, the stress, which they call S, I like to call P for pressure, is the force per unit area. Okay? For both of them. For this first one, the force is 12.0 newtons divided by the area. The area here is 8 by 16. And just doing it in my head, no, I did it wrong, didn't I? 8 times 16, that'd be 48. 128 square centimeters. Okay? Now, if they had just done that, that's not going to be a Pascal. They're going to change this to Pascals. So what I'm going to have to do is, we've got to do a unit conversion here. So let's take that, and someone check me on my math here. 16 times 8, is that 128? I'm doing it in my head. Okay, good. Okay, 128 square centimeters. I need to convert this to square meters. Okay, now notice I always do two lines. First line is for numbers, the second line is for units. Just like this is number, that's unit. This is number, that line will be for number, that'll be the units. Always put the units in their place. Okay, which will go where? We've got square centimeters on one, square meters on the other. Which goes where? One goes above the line, one goes below. Huh? Yeah, square centimeters on the bottom. But I'm going to do what you said. I'm just going to put centimeters there for right now. Don't worry about square centimeters. And we'll put meters on top. Now, let's match the units. What units, how many centimeters make a meter, or how many meters make a centimeter? Anyone remember? What do we call that? And what is it worth? 1 cent. How many of these does it make to make a dollar? 100. Same thing here. 100 centimeters makes 1 meter. Think of that as a centy dollar, okay? A cent, okay? But we've got to square these units, don't they? So we got to square the centimeters, make a centimeter square. We've got to square the meters, make a meter square. We've got to square the 1 to make a square, and we got to square 100 to make a square. Okay? So when you square 100, that gives you how much? Anyone know? Double your number of zeros. There were 2 zeros there, make it 4. 10,000 square centimeters make 1 square meter. 10,000 of these little things to make the area under that door. It's a lot. Okay. Okay. No, those are square inches. A centimeter is about the width of your little fingernail. So just take your little fingernail, that's about a square centimeter. Okay? How many of those does it take to make the bottom half of the door? It takes about 10,000 of them. Okay. So this will be, since you got your unit here, that's 4 digits, so you're going to have to move this 4 digits to the left, so that would be 0.0128 square meters. All right, so that's what I want to put in my denominator here. Now, you don't have to do it this way. The book does it a different way, but to me, this one makes a little more sense. But maybe it's just me, okay? 0.128 square meters, okay? So take your calculator, take 12 divided by 0.0128. You'll see it's a huge number of pascals. .0128. Say what again? 9,375 pascals, or newtons per square meter. But we only have 3 significant digits here, so let's make this 93. There's your 3rd digit. Look to the right. It's greater than, or it's 5, so make this 8. 9380 pascals. 9,000 pascals of stress that brick is putting on the tabletop. Oh, wait a minute. Did I do something wrong here, or did they? Check your thing again. 12 divided by 0.0128.
Oh, 937.5.
All right, so that's 938. I thought that was a lot of pascals. Okay, 938. That's 937.5 pascals. So 938 pascals.
Yeah.
I couldn't believe the book got it wrong. Okay, now we got to do the same thing for this brick. The force is the same. It's just the cross-sectional area is different. So on this one, and if it's okay, I'm going to use the same device here, but we're just going to change this. That one I did do in my head. 6 times 8 is 48. So that'll be 48 square centimeters. If I can find my pen again. 48 square centimeters, but we got to move that decimal 4 places to the left. That would be 0.0048 square meters. Okay, so I'm sorry. I'm sort of mixing this up here. Yeah. Okay. .0048 square meters. Everything else is the same except the cross-sectional area. So the stress for this one is the 12.0 newtons divided by 0.0048 square meters. Okay? You tell me what that is. Second? 2,500 pascals. Now, we would normally call that 2.50 kilopascals. Move the decimal 3 places. 2.50 kilopascals. Yeah. And see, what they had to do was put a bar over that to recognize it. If you go to kilopascals, just putting that 0 tells you that one's significant. All right, you see how that works? Now, they call it stress, I call it pressure. Okay? And there, the next example there is the, let me see if that's in the slides. No, it's not. Okay. Spike heels versus flat shoes. And not just that, they're a lot better for your posture and everything else. Flat shoes are.
Well, I don't know, because some flat shoes make you walk. You know the real flat thing?
Oh, yeah, okay.
I'm flat-footed. Like,
Make
I can
you
feel
walk
myself
funny.
stepping on my hip.
Right.
Yeah.
So I have to wear flat-footed shoes,
Yeah.
like chucks and stuff like that.
Yeah.
If I get a shoe with an arch in it, I have to get the size too small and pull the sole out. Because you know how some shoes be made with that arch on the inside of the foot? My feet be killing me up in that, like where most people got arch.
And I've noticed.
How about heels? Can you wear heels? No, okay.
Yeah.
It's really good for you because actually heels, the reason they do it, designers want women's legs to look nice so men can admire them. But actually that's a very unnatural way to walk, you know, and I just don't see how some of these women make it on those great big old tall, tiny little things, you know, but that's my bias. Okay. What's that?
I said that's why your foot got stepped on with those spikes.
Yeah, exactly. All right. 160-pound woman rests her weight on a 4 square inch heel. Okay. Let's go to the other slide to do that one. Okay. All right. Here is the gal that's wearing a 4 square inch heel. Oops, let me get my pen back.
Let me get the time on the,
What's that?
the time on you. Oh, I see it.
You see it? Okay. All right. This is doesn't have to be flat soled, but you know, a fairly good size heel. And we'll call that, oh boy. Here we have, Barnes, you said? Yeah, Sir Darius? Yeah, okay. That's what I was going to ask if you were Sir Darius, but I couldn't remember. It's been a while. Okay.
I have to catch up when you post it.
Okay, yeah, I'll be putting it up. It should be up by tomorrow sometime.
Okay.
Okay. Maybe even tonight. It just depends on how much time when I get home. Okay. We're talking about stress, which is defined to be force per unit area. That's another word for my mind is pressure, force per unit area. We're talking about someone wearing flat heels with about a 4 square inch heel. So this is 4.0 square inches. Okay. And this gal is a 160-pound woman. So her weight, F sub W, that's weight, force due to weight, is 160 pounds. Now let's see, I've lost it. Where is it again? £160-pound woman. They don't put a bar over it, so only the 1 and 6 are significant. Here it's 2 significant digits too. So what is the stress? If she were to step on your toe, the stress would be 160 pounds divided by 4.0 square inches, and that would be 40, and that would be significant there. PSI, pounds per square inch. That's where that unit comes from. Because you had 2 digits here, 2 digits there, so you need 2. Okay. 40 PSI. Okay? Pounds per square inch. They write pounds per square inch. Just a lot easier to write PSI. Okay. But now she changes to a spike heel, which has an area about like that, exaggerating. We're going to call that a quarter of an inch, square inch. Okay? 1/4 square inches. Well, I don't like to divide by fractions, so let's call that 0.25 square inches. Okay? Much less than the 4 square inches. Okay? Same woman. Now her stress on you, if she steps on your toe, is 160 pounds. Same mass, force, divided by 0.25 square inches. Okay? And what would that come out being? 640 psi. I'd say that's a significant difference. Okay? Way big difference. Okay? You'll feel it big time if you've ever.
She's not like heavy, but she has a little weight.
Yeah. Right. But what makes the difference here is the size of that surface area. I'll tell you, this is a story, and supposedly it was true. I don't know why, but I did grad school in Lincoln, Nebraska. About as close to the middle of the country as you can get, about as far from the Atlantic as it is Pacific, a long way from the Gulf of Mexico. It's about as center as you could get inside land. And yet, people told me that it was one of the waterbed capitals of the world, of the U.S. anyway. More waterbeds were sold there than anywhere else. Well, waterbed, you know what that is? It's the mattress is not made of other materials. It's an inflated tube of water. Okay. Thing of water and held in a frame. Those things, when they're filled up, are heavy.
Yes.
Okay. Well, this landlord had written it in his contract that you could not have a waterbed in the apartment because of its large pressure. So this good old engineering student went to him and challenged that and said, no, if you have a poster bed that has, 4 legs, and say the feet on those legs are about like that, all that weight, just the bed itself without you on it, you've got greater pressure there because your surface area is so small. Whereas the water bed is spread over the entire area of the floor. He did the calculations, showed it. Sure enough, he got to have his water bed that year. The next year, the guy wrote the contract. The weight of the bed, not the pressure of the bed, was too much because the weight was much more. But he got his water bed for 1 year anyway. Okay. And this is exactly why. Now, really what the guy was interested in wasn't the pressure, but the weight, but he wrote it in his contract wrong. So it is important. If you did this using metric units, then she would have been forced you to weight was 65, what did they say? Well, yeah, 65, wait. She's a 65, no, this is not force. This is her mass, is 65, no decimals, kilograms. Okay, her mass, not her weight. Well, to get her weight, how is weight related to mass? What's that?
You have to multiply.
Yeah, by what? M times?
Acceleration.
Due to gravity, mg.
Yeah.
That would be 65 kilograms times 9.8 meters per second squared. Now, you could put 9.80, but we only got, they do 9.80. Doesn't matter in this problem because you only got 2 significant digits there. So you got that divided by, and this time, let's see, a 25 centimeter squared heel. All right, here's got to go back to this. 25 square centimeters. Multiply that by your conversion factor to give you square meters, because you have to have it in square meters to get pascals, okay? And as before, we said the centimeters on the bottom, meters on top, 1 meter was 100 centimeters. Square them, and you get square, square, squared, and this comes 10,000. Which moves the decimal 4 decimal places that way. So that'd be 0.0025 square meters. So she's going to have a bigger number up here and a tiny little number down here, 0.0025 square meters. So figure out how many pascals that's going to be. Okay. While we're doing this, before I forget it, did you get either your first or second test? First one. Okay, but you didn't get the second one. Let me be sure to go on and give that to you, because those came out. I gave those at least, was it last week or week before? Huh? Last week. Okay, but you said you already have the first one. Okay, here's the second one. Okay, I don't think there's any corrections to be made on this. Okay. All right. All right. Still figuring?
254.
254, what, 800? Okay. Now, that is a good, and this would be a kilogram meter per second squared is a Newton, and then per square meter, that would be pascals. Okay? But you have 4 significant digits here. We only got 2 here, 3 there, but 2 here. So we got to limit to 2. So go 2 places. Look to the right. It's less than 5. So this will round to 250,000, 250,000 pascals. Which, if we wrote it in a smaller number, bigger unit, that would be
2550.
No,
250.
250, yeah. 250, what unit? Kilopascals. Yeah, if you make a number smaller, you got to make a unit bigger. So that would be kilopascals. So you see a difference there. I think this was 40 psi, that's 250 kilopascals. So you see, Pascal is a tiny, tiny, tiny little unit. Okay. I don't know if they do it for the, yes, for the small heel, that would be, I should have had you give that number for me, but we'll do it again. The stress for the small heel would then be the 65 kilograms times 9.80 meters per second squared. That will give you your newtons divided by, and this time it's 1 square centimeter. So 1.0 square centimeter. And we know we're going to move the decimal 4 places to the left. So that would be 0.0001 square meter. So divide this by 0.0001 square meter. What's the stress now? If you thought it was a lot of pascals before, what is this one?
637.
637. How many zeros?
4.
I think so. I think that's at least, yeah. So that would be 6,370,000. Well, we have to round this. 6,400,000. That would be, and you could do a couple of things. 6,400 kilopascals, or you could actually call that 6.4 megapascals. I don't know if the book does that. No, they do 6,400. 6400 kilopascals. Huge number. That is as compared to, wow, 6. These aren't exact conversions. A 1 centimeter square heel is probably a little bit, well, yeah, anyway. That's a power of 10 almost. It is exactly a power of 10 there. Bigger number for a kilopascal than would be for a PSI. All right. Now, we mentioned before the rope in a tug of war is in constant tension, and the tension would be the force per unit area. Okay, we were talking about that before. Compression is also force per unit area, and they do have a picture of that one. Let me, no, that's not the one I want. I want this one. And let's go to this one. All right. Here's a bridge. Now, I don't know where this bridge is. I'm not even going to make a guess. It could be, what is it called? The Chapelaya or whatever it is down around New Orleans, north of there. Yeah, that's what it looks sort of like it could be. It could be one that's out in, the reason I say that, you don't have many boats passing under that, because not many boats could get under this one. Whereas in a big bay like Tampa Bay, this wouldn't work. That would block all shipping going to and from. So I was going to guess that one. But you have some others. But anyway, oh, this is the New Clark Bridge crossing Mississippi River. There better be some place that boats can get under that. It sure doesn't look like they can here. Okay? But this is a compressional stress. Whatever the weight is of the highway above that this bridge is holding up, with whatever cars are on, that's your weight pushing down. Of course, the bridge must be pushing up with that, so this is a compressional stress. We hope it's strong enough to hold it, and that's why they have these sections pretty close to each other, so they're not one having to hold so much weight. Okay? But that's a compressional stress, whereas the rope on a tug-of-war would be a tensional stress. There's another kind of stress, and I don't think we have, this is the compressional stress that went with that one. It's the forces pressing inward. Okay? This, though, is called a shear stress. And why is it shear? Because the forces are like this, not like this, so you cause a distortion in the shape. That's a shearing force. So this book is experiencing a shearing force. Friction is keeping it on the table here. You're pushing that way. You're bending the back like crazy here, and hopefully you haven't destroyed the book. Of course, this looks like it's just a manual or something, so it's not really all that important. So that is called a shearing stress. Okay? So I guess I should go back to my slides. Let's see if we have one. Yeah, and this is the example of the shearing stress, just like they had on the book. This is another kind. This is a torsional stress, okay? And that's a twisting motion. Now, I think I mentioned to you before the concept of torque. Same units as work, but it's a different thing. Force times the distance, but this is a torque. Have you ever used a torque wrench? No, okay, well, this is a wrench, and it's under torque because you're pulling this way. The displacement that you are from the bolt that you're trying to tighten up there is here, so that's this force in this direction times the displacement in that direction. That's your torsional force, stress. There's also one called a bending stress. Oh, and this is the torsional stress here. And the symbol for it is tau. It's the lowercase Greek letter for our T was tau. This guy is sitting on a plank. That's called a bending stress. It's both tensional and compressional stresses. And here's where that comes from. Your compressional stresses are the top part of the board. They're being pushed together, whereas the bottom part of the board is being stressed apart this way. Now, if that was too thin of a board, or he was holding in his lap, you know, maybe several 100-pound weights or something like that, at some point the tensional stresses at the bottom are going to give way, and the board will actually splinter and break. Okay? But right now it's a bending force. Okay? I'll go back and give quick definitions of those. So let me go do those first. So let me get out of this, back to my white sheet, and go from current slide and get my pen color back. Okay. Let's go over those again. These are, like say, 5 basic types of stresses. Okay, we were talking about stresses before, and that's force per unit area. The first of these is a tensional stress. Okay, and that's the pulling apart. Stress caused by 2 forces acting in directly opposite each other. All right, okay. Stress, let me get the right word. Stress caused by 2 forces acting exactly opposite each other. Okay, that's the tensional force. The second was compressional forces, and that's when the 2 forces are acting directly toward each other. The stress caused by 2 forces acting directly toward each other. Okay? Tension when they're acting directly opposite each other, compression when they're acting toward each other. Shearing, a shearing force, or stress caused by 2 forces acting parallel to each other, okay, but with a in opposite directions. Okay, so that's a lot like a tensional force when they're opposite directions, but they're not. Okay. Both of those are in opposite directions, but the parallel forces are like that, the ones we saw earlier. They're parallel, one's going this way, one's going that way, but they're parallel to each other, not like this. That would be compressional. This is shear. Okay? And that's going to create a different kind of stress. Okay? Then the torsional forces, okay, these are stress related to a twisting motion. Stress related to a twisting motion. Okay? The force is one direction, the displacement is a different direction, perpendicular to that, and that tends to twist the thing like a bolt. Okay? And then the bending. Okay? The bending is both tensional and compressional. Tensional on the top no, compressional on top, stress, let's see, compressional on top, tension on the bottom. Okay, and we saw the pictures of that. Those are the 5 types of, basic types of stresses. Now, what results from that? Whenever a stress is applied on an object, the object changes ever so slightly. Okay? Remember Newton's illustration? If I push on a rock, the rock is also pushing on me. Well, you can tell where the rock pushed on, or the tabletop pushed on me. What you couldn't tell is I actually did ever so slightly indent that tabletop just a little bit. It bounced right back. It was elastic. Even less here, but I did do some. It really dented me. But you always have some minute amount of thing. Well, that is called strain is a deformation of an object to an applied force. Or it should be stress. Well, they say applied force. Strain is the deformation, how much it's deformed, due to a applied force. Or I'm going to call it a stress. Because stress and strain, they go together. You apply a stress, you result in a strain. That strain could be an elastic rebound. It could be a plastic change, okay, a dent in your car. You know, that's a plastic. It's not going to come back. Or it could be a fracture. You hit it hard enough, it's actually going to break, okay? So that's a strain, the result of that. Finally now, even though we have done some examples, we get our first official example of this chapter. A steel column in a building has a cross-sectional area of 2,500 square centimeters. So the cross-sectional area is 2,500, and that first 0 is significant, square centimeters. Boy, why would you even do that for a steel column in a building? And supports a weight, force due to weight, of 1.50 times 10 to the 5th newtons. Wow. Okay. That is 150,000 newtons. So they write in scientific notation to keep from having to use the units. Okay? Now, remind me, what do we have to do to get a square centimeter to a square meter? Right. And every time we were moving it 4 places to the left, right? And that makes it square centimeter. So I want to go and write this as 0.250 square meters. To me, it's just easier to change that and then do the calculation rather than mix up the unit conversion with the calculation. So this will give you the stress in, find the stress on the column. Okay? So what is stress? Force per unit area. Okay? If you got your units right, which we did already, that's 1.50 times 10 to the 5th newtons. Divide that by 0.250 square meters, and you're going to come up with a pretty big number. Probably won't quite be 1,000,000 yet, but it's pretty close to it. You know how to
I
enter
gotta
the...
figure how to have the square, to do the fifth power.
Okay, I'll show you that. That's
I need to write
that's
that
the
down.
EE or EXP key.
Okay, the EE.
So you put the
second
1.0, I mean 1.5, then do EE or EXP, and then do a 5. That stands for the exponent. And then divide that by 0.25. I think that comes up 6, doesn't it?
Yeah.
6.00.
000. Well, it's 6 zeros, basically.
Okay. 10 to the, is it 6 or? All right. It is 6 zeros after it?
Mm-hmm.
Okay, 10 to the 6. Okay. All right. And that would be pascals. Well, that would be 6.00 megapascals, because 10 to the 6 would be mega. Now, I don't know what they...
I don't know why the book has 10 to the 5th.
Oh, that's what I was thinking. It was the 5th.
But maybe I put this in wrong.
Okay. I was thinking it was the 5th, but when you said... Oops, wait, let me come look. Let me get this changed so it won't be up there wrong too long. Change that too. Okay. To the 5th, which would be 600 kilopascals. Okay, let me... Oh, man, I'm stiff and sore. Okay. Now, you don't do times 10.
You don't?
No. You do 1.5 EE or EXP 5.
Okay, hold on.
That does the times 10 for you.
You have to do it to the second, right? And then do the EE.
Yeah, and just do 5.
5.
And then divide that by 0.250 or 25 will do.
What's the syntax?
Okay, let me see it. I know, you do it. I won't let you do it.
Okay. Clear this out.
Okay.
1.50.
Yeah.
Then you do the second, right?
Yeah, second, EE. Okay.
See, it's got...
No, there's no -1. It's,
That's what they put it up there.
huh?
They put that up there as through the calculator.
Okay. Can you back?
Mm-hmm.
Okay. Back one more time. Oh, wait. Okay. You do a 5 there. 5. Okay. That.
So that's probably the reason why
Right.
it brought that.
Divided by 0.25 equals.
Okay, now it's right.
Yeah.
You see, it was putting that 1 on there. I
Yeah.
don't know why though.
I don't either. Let me look at that one more time.
Because when I hit EE, it put -1 on it.
Oh, you may have hit that key too. Okay, let's. Okay.
Which key is it?
It is this one, but you may have done that and then hit it again a second time without realizing.
Oh, okay.
Okay.
You just hit it one time and then
Yeah.
put the 5.
But yeah, let me try it so I won't be telling you something wrong. I'll clear that. 1.5 second EE and then hit the 6. I think when you said second EE, you hit
I hit it twice.
yes, and it did one time the EE and then the other time the X with the -1.
Oh, okay.
So that's what you were doing.
Okay, got it.
All right.
Okay.
Oh, it's stiff from sitting too long. Okay, so 600 kilopascals. Okay, got it. All right. Now, remember when we were talking about elasticity and we used springs as an example? Well, the guy who did this was a guy named Robert Hooke, a chemist and physicist born in England. He came up with Hooke's law. Just to give you a little bit of background, he was a little bit older than Isaac Newton. So he was an established scientist about the time Newton was coming along. And Newton was incredibly brilliant. So a lot of these established good old boy physicists, you know, here came this young whippersnapper who was just passing them up right and left, and they really sort of resented it. And Newton wasn't a particularly tactful person, so he just bulldozed right on over them. So I think he and Hooke sort of but it heads a few times. Unfortunately, Newton usually won, but, Hooke was a good scientist, a well-established scientist before Newton was even there, but then he got overshadowed pretty quickly. So Hooke's law is the ratio of the force applied to an object to change its length resulted in being stretched or compressed by an applied force is constant as long as the elastic limit has not been exceeded. I really don't want to write all that down, but I will if you think that's important. Would you like to see that written down? No? Okay, thank you very much. Okay, I'll read that again. The ratio of the force applied to an object to its change in length resulting from its being stretched or compressed by the applied force is constant as long as the elastic limit has not been exceeded. Now let's see if they will possibly put that slide up there. This book does a really, that's not the one I want, does a really lousy job of providing good PowerPoints. Okay, that's an example of, they show here of stresses, putting a greater stress on the inside than on the outside, and you get that stretching effect. You're compressing the inner ones and stretching the outer ones. Ha! Here it is. Okay, so let's go from current slide, and I got to get my pen color back. All right. Stomach says it's time to eat supper. Sorry. Why is this not working? There it goes. All right. Here's what Hooke's law says. The ratio of the force applied to the change of, I'm just going to put length, change of area, change of volume, whatever your change is. Usually it's a change of length. That's a constant. And that's called the Hooke's law constant, by the way. Now, lots of things use K, but this is Hooke's law constant.
So do they use the triangle for change for everywhere? Because I know they use that in the hospital. So
yes.
Pretty generic.
What the triangle means is delta, which means difference. Right. The triangle is the Greek symbol for delta, and that means difference. So that means change. Right, exactly. I didn't know they used it in hospitals. That's encouraging to hear that. This is true everywhere in this nearly straight line region. The stress, applied force is here. The change of length is here. The stress force per unit length, that is your Hooke's law. That means that's sort of the slope of this line, not the way we normally think of slope, but it has to do with the slope of the line. As long as you apply a force that doesn't exceed this level here, and you can get this Hooke's law, it's going to come back. But past this, that's the elastic limit, then you get into the plastic range. Now, some materials have almost no plastic range. They are slightly elastic for a little bit, and then you add much more, and they go straight to fracture. That does happen, okay? For instance, ceramics, plates, dinnerware, glasses, things like that, it will do a little bit of elastic, but then it'll fracture really easily. Other things will, and this would be something, I don't know if you remember the old Saturn commercial of the kid throwing the ball in the yard and it hitting against the side of the car, and it pushes the car in, but then it comes right back out. That was elastic. Whereas you can easily imagine I think that's because they had some sort of more of a plastic material in their door, or maybe it was metal, but it just bounced back easily. But if it was a hard metal thing, then throw the ball hard enough, it's going to make a dent, and it doesn't come back, that would be plastic. Or if that was a fiberglass body, and you threw a rock or a ball into it, it might actually fracture it. That would be fracture. So that would be the three. Saturn, they don't even make Saturns anymore, but if it bounced back, that was the elastic region. If it dented, that would be the plastic region. If it broke, that would be the diffraction. One example of all three. So Hooke's law only applies to the elastic region. And that's what I'm going to give you next, is what is Hooke's law. Oh, and that's it right there. Force per unit times the change of length is a constant. Okay? Now, here's example 2. Let's see if they have a slide. No, they don't. Okay? So let me go back to my other PowerPoint. Go to current slide. Actually, I want to go back one slide. Okay. A force of 5.00 Newton. Whoop, let me get my pen back. The force of 5.00 newtons is applied to a spring. Let me sort of draw the picture here. Here's a spring hanging from the top, okay? And you put 5 newtons on it. Nothing's on it here. You add 5 newtons to it, and now it goes down here. So this is 5.0 newtons that wasn't on the spring before. It's applied to a spring whose elastic constant, K, Hooke's constant, or Hooke's spring constant, is 0.25 newtons per centimeter. 0.25 newtons per centimeter. 250. Okay. Now, I didn't do this. I don't want to go back to it. We didn't talk about the units for the spring constant. It's force per unit length. I mean, that's what it was. Remember, the force times the change of length is a constant. So it's going to be some type of force unit, newtons in this case, to some type of length units. In this case, it's centimeters. Now, unless there's some reason, because there's no unit for this, unless there's some reason to do otherwise, let's leave it in centimeters rather than going to meters. And then, you know, if we can afford the changes, let's avoid them, okay, the conversions. So 5.00 newtons, okay? Now, find the change of length. This is what we're looking for. What was the delta L, the change of length? That's your unknown here. So there's one of 2 ways you can do it. You can either plug these numbers in there and then move the numbers around, or you can move the letters around and then plug the numbers in. I call that plug and chug or chug and plug, whichever way you want to do it. Which way you want to move the letters first, or you want to put the numbers in and then move them around. Huh? Numbers? Okay. A little more writing, but it's okay. Huh?
We can do it the simple way then.
Okay. Well, what you're looking for is, what did I put? Oh, that was supposed to be a question mark there, and I don't know how it came out looking like that. Okay. That is the unknown. That's what we're looking for. Okay. If we looking for this, then let's multiply both sides by delta L. Now that gets delta L by itself, and it gets out of your denominator. That's a big reason to do that. And then let's divide by K to get that on the same side with the things you know already. So this says delta L is equal to F over K. And that would then be, force is 5.00 newtons divided by 0.250 Newton per centimeter. Okay. Now, here's how I would do it without a calculator. If you got a calculator, use it. Move this decimal 2 places. That means you have to move that one. 25 will go into 500 how many times? Well, 25 will go into 50 twice. So that would be 20 times. So that's 20 centimeters, 20.0 centimeters. Okay, because here the newtons cancel out, and 1 over centimeter is centimeter. Okay, so that's what I got. Let's see what they, oh, look at that, they got it too. Okay, 20 centimeter stretch. That's a pretty weak spring constant, by the way, so it's a pretty slack spring. Okay. Any questions? Example 2. Okay, example 3 is fairly like unto it. So let's do that one. I almost want to keep this. No, everything's different, so let's don't erase it all. Okay. A force of 3 pounds stretches a spring 12 inches. So let's draw the spring again with no weight on it. And then we're going to do the same spring with 12 pounds on it. And that stretches it. This time they give us a change of weight. 12 inches? Wait. I'm sorry, this is 3 pounds. I misread. Y'all are supposed to correct me. What are you doing, huh? Okay. 3.00 pounds. And this was 12 inches. 12.0 inches. Okay. It's a pretty weak spring too, I would say. What force is required to stretch the spring 15 inches? That's your unknown here. Okay? Now, there's a couple ways you can do this. How would you suggest that we do it? And it's not an additional 15 inches, it's a total of 15 inches.
What about the numbers first, I guess? I don't know.
Okay. Well, where are you going to plug them? What are you going to use?
Force.
Okay. Oh, okay. Force due to weight per unit
Change of the
delta L is equal to K. That's what you're going to use?
Yeah.
Okay. Now, if you're going to use that this way, then do it for what you know. And what that's going to tell you is what your K is. Okay? Now, they're not asking for that. You're asking for this thing here. But you can't get, well, I'll show you in a minute, but you can't quite get there from here. So let's first do this. If you're using this formula, we'll use that. So this will be, just for this one now, the force is 3.00 pounds. That is a force, okay? Divided by your delta L is 12.0 inches. So that makes the K 0.250 pounds per inch. Okay? That's your K. Now, I'm doing that in my head. I hope y'all are checking me, right? Okay.
That's correct.
Okay. Now we can go to this one over here. In this one, we know our delta L, but we don't know our force. But it's the same spring, so it has the same spring constant. So this time it will be F sub W over delta L is equal to K. This time we know the delta L and we know the K. We don't know this one. So do you want to plug the numbers or you want to move the units? Move the letters. Okay. Multiply both sides by delta L. And what you have here is F sub W is equal to K, which was 0.25, 0 pounds per inch. Multiply that by delta L, which is 15 inches. And look at that. Your units come out really nicely, and you come out with a number of pounds. So 1/4 of that would be 3.75. And that would be pounds. And that makes sense. It's got to be heavier than 3 pounds, right? 3.7. It only stretched it a little bit further. So yeah, that seems like it's pretty reasonable. All right. Good deal. Huh? Time to go. We can't squeeze in one more?
That's going to be a long one.
Oh, it's not, is it?
Look, it goes all the way to the next page.
All right. Okay. We will start there next time. Somewhere here I had a pencil. There it is. Okay. We'll start with example 4 next time. Okay. This section does have a few that you can do homework exercises on, which I know you enjoy doing. And it's almost necessary. It's just 1 page away on pages 324 and 325. You can do any of the odds, I would say 1 through 9. Then looks like number 13 is a pretty interesting one. You don't have to plot it, but you can do that if you want to. And then some of the others, 15 through 19. Okay? And then we'll move into properties of liquids. Okay? So tonight we were all in 12.2, which we should have gotten more done than that, but we'll try to move along on the others. All right. Any questions? Okay. Well, then have a good week, and we'll see you next Wednesday. Okay. So let's see. First, I'll